Notice that we're skipping section 2 of chapter 7 because that deals with the structure and function of the eukaryotic cell. And this is your introduction to cells, and we're sticking with the basic simple cells like prokaryotic cells. But all cells are full of aqueous solution. And an aqueous solution is a solution in which water is the solvent. The cytosol, remember that's the liquid or the aqueous solution portion of the cytoplasm, that's an aqueous solution. Plasma in blood, which is the liquid that we're seeing here in this diagram of blood, is an aqueous solution. It's the aqueous solution component of blood. And the cells are suspended and bathed in that aqueous solution. So the environments both inside and outside the cells in this diagram, for example, are aqueous solution. There's an aqueous solution inside the cells, and there's an aqueous solution outside the cells. And the plasma membrane is the only thing that separates those two aqueous solutions. So the plasma membrane acts as a barrier that separates those two environments, those two aqueous solution environments, both inside and outside the cell. The plasma membrane not only separates those solutions, but it also selects. It's selective in what it allows to come into the cell and what it allows to leave the cell. The bottom line is that life is an aqueous solution. Life arose in water, and life continues to have water inside every living cell. Here we're looking at an example aqueous solution, and we're going to use this to try to get across the idea of concentration, the concept of concentration in aqueous solution. But first we review. So a solution is a mixture where the solute is completely and evenly distributed, or dissolved, as we say, within the solvent. The solute is the substance dissolved. In this case, that's salt. And the solvent is the fluid in which the solute is dissolved. And in this case, that's water, because this is aqueous solution. And we're not going to deal with a solution, any solution in which water is not the solvent, because there is no such thing in biology. In this example, salt's the solute, and water is the solvent. So this is an aqueous solution. Water is considered the universal solvent. We learned this back in our biochemistry unit because it's polar, if you'll recall. Water's polar, and it forms hydrogen bonds. And because it's polar and will form hydrogen bonds, it'll form hydrogen bonds with itself, but it'll also interact with other things too, other particles in solution, other molecules and other ions in solution. Salt, if you'll recall, is an ionic compound. When it dissolves in water, or when it's placed in water, it will break up from its solid form, and the sodium ions and chloride ions will dissociate and distribute themselves in solution. But notice how the water molecules are interacting with those ions. So here's a chloride ion. It's completely surrounded by water molecules. And the same with the sodium ions. They get completely surrounded by water molecules. And if you look closely, you can see that the water molecules are turned in a different orientation depending on the charge of the ion. So sodium is positively charged and chloride is negatively charged, and the water molecules are orienting themselves differently because of that. So now we get into the concept of concentration. Concentration refers to the, and we're going to use this symbol to represent concentration. So a bracket around something is going to mean the concentration of whatever is within the bracket. So in this case, S is standing for solute. So you would read this, the concentration of solute, right? So wherever you see a bracket around something inside the bracket, it's the concentration of whatever is inside the bracket. So it's the amount of solute dissolved in the solvent. That's concentration. So if you put more salt in water, that's a higher concentration of salt, higher concentration salt solution. If there's less salt dissolved in the water, it's a lower concentration salt solution. So a solution with more solute is more concentrated relative to a solution with less solute. And we usually refer to a solution with less solute as dilute. So a dilute solution is a solution that it has relatively low concentration. Or if you have a high concentration solution, you can make it more dilute by adding more water. So concentration is measured and calculated as the mass in grams or number of particles in moles. And you're going to learn all about moles in chemistry next year. All you need to know about it now is it's a way of indicating number of particles of a substance. But it's the mass or the number of particles per unit volume. Now, for our purposes, we're always going to just use the mass, not the moles, because again, that's a subject for chemistry next year. So mass divided by volume. Concentration is calculated by mass divided by volume. So in these example calculations here, if we take 100 grams of sodium chloride, salt, and we dissolve that in 1 liter of water, we've got a solution then that has a concentration of, and this is pretty simple, you can probably figure it out for yourself, 100 grams per liter. Right? Because we took 100 grams and put it in 1 liter of water, so that's 100 grams per liter. Similar calculation, and the way you can calculate that is 100 divided by 1, right? Mass divided by volume. 100 grams divided by 1 liter is 100, right? 100 grams per liter. 10 grams in 100 milliliters of water, you can just go ahead and divide that, 10 divided by 100, and the units are going to be in milliliters instead of liters, but that's 0.1 grams per milliliter. Now, if you convert that to grams per liter, you'll find that because there are 1,000 milliliters in a liter, you multiply by 1,000 in other words, and that's 100 grams per liter. So in other words, 0.1 grams per milliliter is equivalent to 100 grams per liter. So the bottom line is that concentration is the mass or number of particles per volume. That's what indicates the concentration of a solution. This slide is, and diagram is to try to get across the idea of diffusion. Diffusion through cell boundaries, but we're not looking at a cell boundary yet. We're just looking at this concept of diffusion. So in this diagram, this person is placing 1 drop of dye into water. Relative to the rest of the container, the dye concentration is very high only where the drop first enters the water. In other words, this represents a very high concentration of dye. And we can symbolize that using our bracket. So an up arrow in a bracket means high concentration of dye. The D inside the bracket represents dye. That means everywhere else in the container, there's a relatively low concentration of dye. And actually, there is none. So it's a very low concentration of dye, so low that it's actually 0. So that means that there's a concentration gradient here from where there is a high concentration of dye to where there is a low concentration of dye. That's what we call a concentration gradient. So a concentration gradient is simply a difference in concentration between locations within solution, or, as you'll find out, across a membrane. A difference in concentration between locations in a solution or across a membrane. So in this case, we have a concentration gradient, and we're going to symbolize that with a lowercase g subscript on the bracket. So you want to read this as the concentration gradient of dye, right? Because the D in the middle is dye. This represents the concentration gradient of dye in this container. As time passes, the concentration of dye is still high, relatively high in the location where the dye drop was first put in, but you'll notice that those dye particles, those dye molecules, are starting to diffuse. They're starting to move from where there is more of them to where there is less of them. So there's still a relatively low concentration of dye over in this part of the container. As time passes, the dye molecules move along their concentration gradient from high concentration to low concentration. And that's the way diffusion always happens. It always happens from high concentration to low concentration. We call that along the concentration gradient. So all particles in solution are going to diffuse along their concentration gradient from high concentration to low concentration. So there's still a concentration gradient here of dye molecules. And then finally, we get to the end here, or enough time has passed so that the molecules of dye have evenly distributed themselves within the container. So there's equal concentration throughout. There's no concentration gradient, and we refer to that as equilibrium. Equilibrium is when the solute particles are evenly distributed within the solvent, and there's no concentration gradient. So what we have here, once we reach equilibrium, is an aqueous dye solution. It's an aqueous solution of dye particles or dye molecules that have evenly distributed themselves. So the bottom line is that particles diffuse along their concentration gradient to equilibrium. So now we need to add the component of the plasma membrane, because this is, remember, this is all about cell structure and function. So because cells have this aqueous solution inside and an aqueous solution outside, and remember the plasma membrane is the barrier between the two. So just to review here, all cells have DNA and cytoplasm and ribosomes and a plasma membrane. But not all cells have a cell wall. So what I want to do here is just make sure that you're very clear as to the difference between the plasma membrane and the cell wall. The plasma membrane is a flexible, fluid, selective barrier between the aqueous solutions inside and outside the cell. Flexible and fluid. Whereas the cell wall is rigid, and it is outside the plasma membrane. So it's in addition to the plasma membrane, because all cells have a plasma membrane, but not all cells have a cell wall. And those cells that do have a cell wall, it's in addition to the plasma membrane and outside the plasma membrane. So cells of the kingdoms Archaebacteria and Eubacteria and some protists and fungi and plantae all have cell walls. The plasma membrane again functions as a selective barrier, while the cell wall functions in protection, support, and to maintain shape. So that's what I wanted to make very clear to you. There's a big difference between the plasma membrane and the cell wall. So the bottom line is the plasma membrane is a selective barrier. Well, what's the plasma membrane made out of? Well, all cell membranes are made out of the same thing, basically the same thing. So cells in general are largely made up of membrane. Cells are mostly made up of membrane and proteins. The molecule in the top left of this diagram, this is a phospholipid. And this shows all the atoms that are involved in making one phospholipid molecule. The two major regions of this phospholipid is the polar head, which is hydrophilic. So this is the polar head of this molecule. Hydrophilic means it's water-loving. It interacts well with water because it's polar, and water's polar. And there's also the hydrophobic tails. These, if you'll recall, well, this is a lipid, and if you'll recall, lipids have fatty acids, so these are fatty acid tails coming off of this phospholipid. And they're all made up of carbon and hydrogen, which makes them nonpolar, completely nonpolar. Therefore, they don't interact well with water, which makes them hydrophobic. So the tails here are hydrophobic, water-fearing. There is another representation of the same thing here. So in other words, this is the same molecule, just a different representation, not showing all the atoms, just showing the hydrophobic head and the hydrophilic head and the hydrophobic tails. And then in this diagram, we see what happens when we place phospholipids in water. They form a liposome. And if we zoom in on, just one portion of the liposome membrane here, that's what we're looking at here, and we can see that these phospholipids have arranged themselves in kind of like a sandwich, where the hydrophilic heads are like the bread of the sandwich on the outside towards the water on both sides of the membrane, and the hydrophobic tails are pointing inward and trying to get as far from the water both inside and outside as possible. So this happens automatically. When you place phospholipids in water, they just automatically form this structure that we call a phospholipid bilayer. 2 layers of phospholipid molecules. Bi means 2, right? Bilayer. So it's a phospholipid bilayer that kind of looks like a sandwich. But they automatically fall into this arrangement because of their interaction with water. Water is what causes them to react this way and form this phospholipid bilayer. So the bottom line is that all cell membranes are phospholipid bilayers, whether they be the plasma membrane or the membranes that surround the nucleus or the membranes that surround organelles. So now we're going to put the 2 concepts together, diffusion and the plasma membrane, and how particles will diffuse across the plasma membrane. So in this diagram, this represents the plasma membrane. And we've got a solute that's dissolved in solution outside the cell versus inside the cell. So extracellular refers to outside and intracellular refers to inside. And those are vocabulary terms you need to be aware of. But this membrane is permeable. There's another vocabulary term, permeability. This membrane is permeable to this solute. In other words, the solute's able to pass through the membrane. And general characteristics to be able to do that are that the particle needs to be really small to be able to fit in between the phospholipids and making up the phospholipid bilayer. It needs to be relatively small. And it's best if it's nonpolar. It can best interact with the nonpolar tails of the phospholipids and get through the membrane if it is nonpolar. So small and nonpolar particles are better able to pass through the phospholipid bilayer. But if it's small enough, even if it is polar, it'll pass through. So for example, water can can relatively easily pass through the phospholipid bilayer. So this is just defining extracellular and intracellular. So what we've got is a high concentration of solute, right? S for solute. High concentration of solute outside and a relatively low concentration of solute inside. And you know what that means. That means we have a concentration gradient from outside to inside. Concentration gradient of solute. As time passes, because the membrane is permeable to the solute will begin to diffuse across the membrane and pass from the extracellular environment to the intracellular environment. We still, though, even after a relatively short period of time, we still have a higher concentration outside versus inside. So net diffusion, as we say, of the solute will continue from outside to in along its concentration gradient. So there's still a concentration gradient here, and diffusion continues along the concentration gradient as time passes. Finally, eventually, the concentration of solute outside is going to be equal to the concentration of solute inside. And of course, we call that equilibrium. So eventually, the solute concentrations equal out across the membrane, and at that point, we have reached equilibrium. So there's no solute concentration gradient at this point. However, the particles still diffuse across the membrane in both directions at the same rate, but there's no net diffusion. There's no one direction change in concentration across the membrane over time. It stays the same because the same number of particles that diffuse in also diffuse out. So there's no net change. But we call this a dynamic equilibrium. Dynamic means that things still move, but there is no change. It remains at equilibrium. So the bottom line is, this is known as passive diffusion because it does not require energy. So passive diffusion requires no cellular energy. This happens all by itself. Really where the energy comes from is heat and the kinetic energy of the particles in solution moving around.